Join with computer audio. So I might be able to record something this week or today. Whatever the assignment in the, so it, yeah, if Canvas says something, then I'm going to make sure that it follows that. But yeah. Yeah, I think the Bode plot ones might not have automatically. I'll have to check it and make sure, but yeah. Okay. Okay, then set this up. Okay, so I'm going to try to show these two examples real quick. I said I was going to record these. Hopefully I can get through them both. So the first example I wanted to do is actually this one in the middle. Let me zoom in a little bit more. Okay, so in this example in the middle, I've chosen the input side to be flat, which makes it very easy to keep track of what we want. So what I'm trying to do is take this graph and I want to write down an expression. So this one, I'm going to call this one the magnitude of H1 of j omega, right? And so I'm going to write down what actually is H of j omega going to be. Now, technically, I can't determine this unless I know what the phase is. We could have some random j running around that is just extra sitting in there. So technically, I can only really determine the magnitude from the magnitude plot, but we're going to assume that everything's standard. If there is an omega, it comes with a j, and that's the only place that the j's appear. If we just put a loose j in the expression, we're technically allowed to do that, but it wouldn't result from a circuit. So we're not going to have that happen. So for this H of j omega, we can see that there are a few critical values. And so we know what the form of this is going to be. So there's going to be a leading K. Since this input side is flat, there's not going to be a j omega in either the numerator or the denominator. In my second example, there is going to be an extra j omega because we're starting at a slope. But if we're flat, that means that there is no pole or zero at zero, creating an initial slope. So in this case, we're just going to have a k, and since it's flat, the k can be determined entirely from this value that our thing is at 10, and we'll deal with that shortly. But we'll calculate the value of k in a moment. So there's two ways that we could write H of j omega. And for this one, I'm going to show you both methods. And then the second example, I'm just going to show you one way of expressing it, because the point of the second one is to have this initial slope and learn the trick for dealing with that. So for simplicity, I don't have an initial slope, so there's no j omega here or here. It's just going to be a capital K. I can also start to incorporate these zeros and poles into my expression. And so I'll save the determination of value K for later, though we certainly could start with it. So I see there is a pole creating a minus 20 dB per decade slope at, on this graph, it appears to be, this is 10 to the 1, and this is 10 to the 2. So running back, that's going to be 90, 80, 70. This is 10. This is 100. On a log scale, back from 100 is 90, 80, 70. So we can see that there is a pole at 70. So we're going to get a 1 plus j omega over 70. Then this slope continues until this point, where we get another plus 20 dB per decade to counteract the minus 20 we already have and turn this flat. So because our slope changes here at this break, it goes from minus 20 up to 0 dB per decade. That tells us that there is a 0 at this point, creating that break. And so this is located at the 700 point, because again, this is 100, this is 1,000, count it back, 1, 2, 3. This is at the 700 point. So this is 1 plus j omega over 700. Okay. Then this continues. Okay, this point is at the 7,000. And so I kind of chose this to have nice numbers. So here's 10,000, 10 to the 4. So it's kind of hard to read, but this is 10 to the 4, 10,000. This is 1,000, which is 10 cubed. This, I forgot to change the size of the numbers. This is 100, this is 10. Okay, so I'm just reading off these pole and 0 locations. Then at this point, which is on the line of 7,000 here. So at the point 7,000, our slope goes from 0 to minus 40. So that means there is a double pole here. If it went from 0 to minus 20, we would have a single pole at 700. But since it makes a double-sized break to minus 40, let me make sure I'm recording this. Okay, it should be good. My audio is on. Okay, yeah. So it makes a double-sized break from 0 down to minus 40. And so that means there is a double pole in order to get us the minus 40. And so this is 1 plus j omega over 700 squared. Okay, since there is no sketched resonance peak, this is just the straight line approximation. I'm going to use the double pole form. If you distribute this out, you'll get the zeta equals 1 quadratic form. If you just distribute the square. Since there's no resonance peak, you don't have to use the full form, quadratic form, and determine the size of zeta by the size of the peak. I'm not going to have you worry about any of those. So you can assume in my graphs here, and since it's not shown, you can definitely assume, even if we weren't assuming, just because I can tell you that I'm not going to make you do the quadratics this time or in any of the test questions or anything. But even if I didn't tell you that up front, the lack of a sketch of a resonance peak allows you to just assume zeta is 1 and either write the quadratic form with zeta equals 1 or write it as a square. So this is the standard form. And what's nice about the 1 plus form is as long as you are to the left of the pole or the 0, these terms act like 1. All of them act like 1 as long as the frequency is earlier than any of the poles or zeros. So if we're off to the left here of our first pole, all of these act like 1s, and they contribute 0 dBs because it's just k times 1 times 1 times 1, as long as we're to the left of all our zeros and poles. So we're able to read the exact value of k from this 10 if we write these terms all in the form 1 plus j over pole, 1 plus j omega over 0. In some of the homework questions, it asks you not to write it in this form, but I would still recommend starting from this form because it allows us to read off k immediately. So I'm going to convert to the other form in just a moment. Before I do that, though, I can calculate the value of k in this expression. If we're to the left of all our zeros and poles, these all act like 1s. And so the value of k is readable from the value where it's flat here. So I know that this is 10 dBs. So I can know that k is equal to, we take the 10, we divide it by a 20. So what, okay, the full calculation would be, we know that 20 log base 10 of k must be equal to 10. And so then solving this, we divide by 20, take 10 to the power of 10 over 20. Oh, you can't see that, sorry. So the K value, now that I've drawn in all the terms for poles and zeros, we know that 20 log 10 of K is 10. That means that K must be 10 to the 1/2 power. And so then K is approximately equal to 3.1. That's as far as I remember radical 10. Let me open it up real quick and get a better approximation. So radical 10 is 3.163. It is a little bit better. And so if I want, so then in the full expression, this would be like 3.163 or just radical 10. If I wanted to put it in an exact form. So for this one, I'm then going to convert to the other format. I'm not going to make it to get coffee before my next class, which is fine. I don't need coffee, but okay. I really wanted it though. Okay, so maybe I'll just get a tea. Anyway, so this is the easy form to write based on the graph, but sometimes you might be asked to put it in the form that looks a little bit nicer in terms of j omega plus pole. That looks very nice as an expression. So I would recommend getting this expression and then converting it to the other form. Okay, so what I'm going to do is modify these terms one at a time. Okay, so we have h of j omega. So up front, we're going to start with a 3.163 or radical 10. And I'm going to modify the terms one at a time. So I would like to convert this to the form 700 plus j omega. I need to zoom out now, which is fun because I'm not looking at the graph. So I want to take this term, 1 plus j omega over 700. The other standard form is to write it as j omega plus pole. So if I'm introducing a 700 here, I have to place a 700 in the denominator to counteract the multiplied 700 that I'm putting in here. So I'm taking this term, multiplying it by 700. So I have to take the coefficient and divide it by 700. So I don't change h of j omega. In the denominator, and so I'm just going to kind of leave this off to the side. So I kind of pulled the coefficient out front, and then I'm going to modify the terms, writing the correcting coefficients over here. You can just kind of multiply. You can also just think about it as, oh, I multiplied the numerator and the denominator by 700. And then I took the 700 in the numerator and brought it into the term. But the 700 in the denominator has to stick around. Oh, sorry, and this is supposed to be 7,000 all along. Sorry about that. Our last pole location was at just short of 10 to the 4, so a little short of 10,000, so it's 7,000. 70, 700, 7,000. Sorry, I didn't notice that. Okay, so I've corrected my numerator. I can then modify the denominator with a 70. So this is going to be 70 plus j omega. So I put a 70 in the denominator. By doing this, I need a 70 in my numerator. Okay, so there's my 70. Then I've got 2 copies of this one. So I want to write this as 7,000 plus j omega squared. And so each of those has a 7,000 that I'm sticking in the denominator. And so I'm going to need 2 7,000s in the numerator to counteract the 2 7,000s I put into the denominator. And I really should have written this further to the right because I want to put the coefficient out front, but I'm going to drop my coefficient in here. This coefficient is, okay, so the 3.163 is radical 10. I'm going to try to get a good approximation. So we've got radical 10, we've got 7,000 squared, we've got a 70, and then we've got to divide it by 700. In order to make this work. So I'm going to calculate that out. Okay, so I've got radical 10. I've got 7,000 squared. I've got 70, and I'm going to divide it by 700. And so I'm pretty sure the correct calculation, and I didn't do this up front, and I really should have, because then I would be guaranteed that I've got the correct. Where did I write? I've been using the black pen. I'm going to need it in a minute. I don't know where I set it down. Where did it go? Is it in my pocket? No. You're going to be watching this recording and see where I put it. And now I'm going to look ridiculous for not knowing where I set it down. Oh, okay, it's hiding in this. Yep, it's been right here the whole time. Okay, so now that I've looked completely silly, that is, so this is 1.55 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 7th. And so this does match my intuition of what I would expect this to look like. I'm very confident that this is in fact the h of j omega. Assuming everything's standard. What I was saying is I could throw a random j in here for no good reason. And technically, the magnitude would be unchanged. So I could even throw e to the j something, anything of magnitude 1, I could theoretically throw in there if it's not banned, but I'm not going to do that. We're going to assume that there's no loose j's or loose exponentials running around. Any j is attached to an omega, but because that's how it works in circuits. You don't get extra j's running around, but okay. It's always a j omega everywhere that j appears. Okay, but I just wanted to note that because it's theoretically possible, but we're just going to assume that the phase does normal stuff and there's no weird phase modifier. So this is what we would get for h of j omega. You can either write it this way or this way, and they're both perfectly good, although this is the easiest one to extract from a diagram as quickly as possible. And it's also the easiest one to put onto a graph as quickly as possible. But this one looks a little bit more appealing, so it still persists as an option for how to graph it or for how to express it. So example 2 that I wanted to hit is this particular Bode plot. And okay, so this one doesn't have its slopes marked, but it's pretty clear overall. So I'm just going to mark our critical points. So there's a critical point here at 100 radians per second. That's the horizontal here. Then this point is at 200, 300, and I'm just reading the axis here. And so then this is 1,000, 2,000, 3,000. And these are all radian per second. So I'm looking at particular frequencies. So the challenge to this one is getting the correct K value. So what I know is that we are starting at plus 20 dB. So there's going to be a K value and there's going to be a J omega. And so this J omega is a 0 at omega equals 0 that is creating this initial plus 20 dB per decade slope. And it persists over all frequencies. So that's why it's just J omega alone. As omega changes, the magnitude always changes, no matter, there's no real term to dominate for small enough frequencies. The omega term is the only term there is. And so that's how we get a plus 20 dB per decade slope. that exists everywhere. So the challenge is going to be to find the value of K. We know that there must be a pole at 100. So I'm going to get a 1 plus j omega over 100 because our slope goes from plus 20 to flat. So that's a minus 20 dB after the break at 100. At 300, we get another break of minus 20 dB per decade, taking us to an overall minus 20. And so we get 1 plus j omega over 300. And then from minus 20, we get a break that takes us to 0 at 3000. So this is 1 plus j omega over 3000. And that's fine. So the trick is to find K. That's the part that makes this messy. Okay, so on this slope, you can choose any easy to read point that is to the left of all of the non-zero zero and pole locations. So if you're to the left of all of your corners, find a point that you can measure. And so I'm going to go right here where I am at the point 10 radians per second, comma, minus 20 dBs. And there's a space I didn't write radians per second, but we're talking frequency. I should be zooming in here, sorry. So I see this point, it's to the left of all of my corners, and it's at a frequency of 10 radians per second and a height of minus 20 dB. So when I'm to the left of all of the corners, these three terms are approximately 1. So these have no effect whatsoever. So if I plug in omega equals 10, I know that h of j omega fits this form. And I know if I plug in omega equals 10, this is approximately 1. This term right here is approximately 1. These two denominator terms are approximately 1. I know that there is a j omega equals 10, and there is an unknown k. And this is h of j10. But I have this point here. I know what h of j10 must equal, or at least what the magnitude of h of j10 must equal. So I am guaranteed, using our point, that the magnitude of h of j10 must be minus 20 dBs. H of j10 written in dBs must be minus 20. Sorry, now I'm still zoomed in. I'm having Zoom troubles today. Okay, so h of j10 in dBs is minus 20 dBs, which we can just read from the graph itself without too much trouble. So you could choose, I mean, you can do the same analysis at the corner. It's a little bit uncomfortable to do it at the corner because we know that the straight line approximation is not great there. So technically we're fine because we're only using properties of the straight line approximation, so it doesn't matter. But I put it all the way to the left just to be super safe, even though I know I don't need to. So we get that h of j10 must be minus 20 dBs. So I need to take the magnitude of this, which the magnitude just removes the j. And so I know that the magnitude of h of j10 must, it doesn't want to zoom in, it's not focusing. Come on, focus. Okay. So I know that the magnitude of h of j10 in raw magnitude is just 10 times k at frequency 10. Okay, so then I know from the dB formula that 20 log base 10 of 10K must be equal to minus 20 dBs. So solving this, I know that log base 10 of 10K is equal to -1. And then I cancel the dB units. Suddenly this side also has dB units. So it's 20 dBs log 10, 10K. This carries the dBs, but the left side's in dBs too. Doesn't matter, unit tracking stuff. But set this equal to the minus 20, divide the 20 over. So log base 10 of 10K is -1. Log properties tell us then that that means that 10 to the -1 power must be equal to 10K. 10 to the -1 is 1/10. And then we divide the 10 over, therefore K must be equal to 10 to the -2. And so all the way back up at the top, I can replace the K with 10 to the -2. And so that's just a consequence. The complication that results from having a slope instead of a flat. When it's flat, you get to read it directly. When it's a slope, you have to pick a point, plug in, pick a point to the left of all of your breaks, plug that point in, and solve. You can do this when it's flat. It's just that when it's flat, there is no J10 to plug in. And so it's just K times 1 times 1 over 1 times 1 and all of that. So when it's flat, you just get to read K because all your terms go to 1. But when it's at a slope, there's an extra J omega. And so you need to pick a point, plug in that omega, figure out what the dBs are at that point and solve. But that's the only challenging bit there. And then from here, you just, if you wanted to get to the other form, you just manipulate it in the same way that I described in the previous example. Okay, and it's 2 minutes to class now, so I just barely made it. I'm not going to get my coffee, but that's okay. And so maybe I'll still snag it on my way out. All right, I hope this helps. I'll be posting this on the YouTube, on my ASU YouTube shortly, or probably after class sometime this afternoon. And then you'll see this. So hope you all are having a good weekend and good luck on the final next week, if we're in the final next week. But maybe we're in a later term where I'm running a little bit further ahead and we don't have finals next week. But well, anyway, for my students this term or next term or whenever, have a good weekend and I hope everything's going well. Bye-bye.